Okay, it's recording. And Sudesh, so you should be a co-host. So feel free to share your screen. And thanks so much for doing this.
Can you all see my screen? Okay, guys, thank you all for coming. So this is a bit of presentation, and there'll be some activities. There are two activities in this presentation, so it kind of makes it like presentation and workshop, you can say. The idea is not to go too much into details, but kind of just give you a flavor of different things that's out there for optimizing the code, so that you can explore it. And maybe in the future I'll maybe do a second part to it if I get time. So first I'll start with basically just some terminology that we'll be using for basically memory operations. I'll kind of give you an introduction to how mathematical operations take place in the CPU. After that, I'll talk about, we have some Python activities, but we'll mainly talk about how you can optimize for loops. You can write like basically alternatives to for loops in Python. And then in general, for loops, there'll be some tips for optimizing for loops in other programming languages. And then some final remarks on when should you optimize your code. So when I think of code optimization, I basically think of three components to it. One is you can optimize the data structure and the algorithm that you're using. The other is code implementation, how you're implementing your code. And third is how can you tweak your code based on your specific hardware that you have. In this presentation come workshop, I'll be mainly talking about the second part, which is code implementation. As you all know, there are many components of a computer. You have the CPU, memory, storage, keyboard, and everything. Here I'm making a distinction between memory and storage, but they're kind of same. But memory more in terms of like we'll talk about it. But there's RAM, storage more in terms of a hard disk. The other terminology that I want to talk about is registers and cache. You might have at least heard of cache if you have kind of purchased a computer on your own. There's L1 cache, L2 cache, and L3 cache. Both registers and cache, they are actually present on the processor chip that you have in the CPU. But the idea of cache is basically to hold data for any operations. So it kind of acts as a link between your hard disk or your storage to the central processing unit. Registers is closer to the CPU, and it's where all intermediate operations like if you're it's kind of the memory in the CPU that's the closest to where the operations is happening. And registers are typically not typically, they are always faster than cache. But they will have a smaller width within the sense of like how much you can store on the registers. The other one last terminology that I will use is clock cycle. So basically any operation that happens on your computer, they need to be synchronized. And so the fundamental unit of measuring time is basically clock cycle. Like any operation has to take at least one clock cycle. Addition typically takes 3 cycles, multiplication takes 6 cycles, and division can take like 30 to 60 cycles. These depend on different stuff, but this is a general, you get the general idea that, multiplication and division takes a lot more cycle than addition. So let's talk about a basic operation where you are adding y and z. and saving it in X. So what happens first is your operating system fetches instruction from the memory and has to decode it. And when that fetching is happening, it's basically you're fetching the instruction from the hard disk, which goes to the RAM, and then it goes to the cache and registers, basically inside the CPU. And this takes around, might take around 300 cycles or something. So compare that to, what the operation itself takes. Then you fetch the data Y and Z from the memory, which again takes, 300 cycles. And then you perform the addition. And this takes, as I mentioned earlier, around 3 cycles. Do you all notice some things here?
Fetching the data is the slow part.
So, sorry?
Fetching the data is much slower than the actual operation.
Yeah, in other words, the actual operation itself is taking hardly any time compared to the whole total time, right? Like the total time is around 603 cycles or something, right? But the actual operation takes only 3 cycles, right? So let's move on to, and before that, think of this as a, this whole thing as a stages of a pipeline. So these can happen only sequentially because the registers itself, the memory is small, so you can't do everything simultaneously. So you have to first fetch instruction in the register, then fetch data in the data register, and so on. So these happen sequentially. Now consider instead of just doing Y plus Z, you have a list of numbers in Y and a list of numbers in Z, and you are adding it element wise, right? Now, if you think about the operation that I talked earlier, then it would take what? Each operation there took 603 cycles, right? So if I do it n times, that would mean that I'm taking 603 times n cycles, right? So there's a lot of wastage here. So can we do better? Any ideas on how we can do better?
Well, if you could parallelize it, so each of them, if x of I plus 1 doesn't depend on x of I, then you could do all of them simultaneously.
Yeah, there are 2 important points that you basically mentioned. One is, what is kind of called data dependency. So since your Y and Z are not, your successive iterations are not dependent on each other, you can parallelize them. And the second part was basically parallelize them. The problem with that is, one issue with that is, even if you parallelize them, one is that the register itself, they are not wide enough to do parallel operations, like a lot of parallel operations together. And the thing is, you are still basically you are fetching them in 300 cycles. So even if you parallelize them, kind of, you are still getting using 600 cycles just to fetch the data instruction for that, right? So you can do better. This is something like kind of, if you have a machine line, so you can use data streams. Basically, instead of sending Y1 and Z1 first, and then like waiting for 300 seconds, you can send that as in a whole stream. So the only latency that happens is with the first one, right? Because once you send them as a stream, you use just 600 cycles to fetch the whole stream, and then you add Y1 and Z1 to get X1, and then the next one is immediately available, right? And so this is kind of what the compiler or operating system does. And the other way you can reduce a bit more is you can fetch the next instruction while the previous instruction is executing. So you can do this better, and so that way you kind of reduce that 300 cycles for each of your elements. So you reduce what 600 times n-1 cycles of operation. So you're kind of speeding it up a lot. Can you do even better?
Can you do it in a pipeline fashion, the way you described, like the 300, and then within the first 3 cycles you do the addition of the first, and then yeah, I mean the way you described it is, I guess,
these are pipeline.
These are the pipeline, right?
Yeah.
Is there a way to like fetch all of them in one way and then just like loop over the components and just do the addition, which takes 3 cycles? So it takes like 600 cycles to fetch all the data, and then you loop over each individual component, which takes like 3 cycles. So it takes like 600 cycles plus 3 times n.
Yeah, so that's what the pipeline thing does, right? The pipeline and data stream, that's what it does, right? You fetch all of the data.
No, and in the pipeline, yeah, the way I understood is that you fetch like the first y1 z1, and then you shift like the other one by 3 seconds to do the addition. And then you read the second one after you finish the addition, right?
Okay, yeah.
I guess this is how the pipelining works.
Yeah. So what was this second thing that you mentioned?
So my idea is there a way to fetch like the whole data and like 1 in 600 cycles, like the whole vector y and the whole vector of z?
Yeah.
Just do the addition.
Yeah. So that's the second. You can do even better. What's called basically vectorization. So for that, you have several things that happens in vectorization. One is vector instructions. So here, previously you had, for every addition, you had an instruction. In vector instructions, you have what's called one single instruction for multiple. The earlier, you can think of that whole thing as a cache line. And in a vector instruction, you operate on several cache lines with a single instruction. And also, there are vector registers which can hold multiple cache lines at the same time. So you can, you can do all those operations with single instruction simultaneously. Okay, so this is more. This is a bit of a hardware requirement too, actually. And also, you can do this only if you're, as Rachel pointed out earlier, your data is not dependent. So what the compiler basically does is, if you write your code in a, kind of a vectorized form, then it will unroll your loop. So earlier you had, xi is equals to yi plus zi, and you're iterating from 1, 2, 3 to n. Now, instead of that, the compiler changes that whole instruction to xi is equals to yi plus zi, and you're inside the loop, you have xi plus 1 is equals to yi plus 1, xi plus yi, xi is equals to yi plus zi, and then xi plus 1 is equals to yi plus 1 and zi plus 1, and so on. And all these 4 operations are happening simultaneously because these are not dependent on each other. They can happen simultaneously in the vector vector register, and then you update your I to 5 instead of 2. So you get that speed up here. So this is the idea of vectorization. We'll talk a bit about vectorization in terms of in the context of Python. Next, we have some Python activities planned, but before that, does someone know why Python loops are slower compared to the similar loops in Java or C? So Python compared to Java and C or C++, Python is an interpreted language, while Java and C are compiled languages. In interpreted languages, you can't kind of look ahead in the future. So every instruction is, kind of execute, like you wait for the instruction and happens like at runtime. So every loop you are kind of, translating into machine code during runtime, and then that kind of makes it slow. It's not a good explanation, but that's how I kind of understand it. While in Java, because of its very strict typing and everything, you can kind of look ahead into what's happening in the future. I could give a better example if, in a question and answer session if someone wants, but for now we'll just So if loops are like really slow in Python, what are the alternatives to using loops in Python? So one is list comprehension and set comprehension. So if you have attended Brent's PyOmo tutorial, you might have done a bit of comprehension in that, most likely. We'll look at some examples, but yeah. Then other is vectorization using the Numpy library. The Numpy library, basically, it's a highly optimized library, and the code itself is written in C. So that kind of makes it possible to compile it and then use vectorization and stuff. In my demo, we'll do some demo on these things, and then we'll do an activity too. But in my demo, I'll just use some simple examples. But for vectorization, if you want to use vectorization, in complex scenarios, then you'll also have to look into what's called broadcasting. We'll not go into details here, but you can look it up and learn how to do broadcasting. And the last one is just-in-time compilation. It's kind of basically compiling the code instead of interpreting it in some way, and that makes it faster. We'll look at examples. And then later we'll also talk about tips on optimizing your for loops if you are stuck with a for loop. This is your first activity we'll have. So here I'll give you 5 to 10 minutes to do this activity, and until then I'll take any questions you have so far. So the activity is basically you have to write a Python function to generate exponential smoothing prediction of the given series of this series, and your alpha value is 0.1. You can, if you don't know about exponential smoothing, you can look it up online. But this is the basic formula. An exponential smoothing kind of predicts a time series. It makes prediction using a weighted average of your current observation and previous forecast. Just make sure that once you've written your function, your Python function should return this approximately this value. I'll give you 5 to 10 minutes, and then until then I can take any questions you have so far. And also make sure to time your function using the time it module or magic function, depending on whether you are using Jupyter Notebook or text editor to run your code. I realized that I actually forgot to do the demo for those three. Let me, where's the, yeah, so I'll actually wait for you all to finish up with your coding that you're doing, and then we'll do the demo, and then we'll get into the discussion about the activity. Does that sound good? By the way, I picked this question up from basically when I was interning at Sabre back in 2019. I kind of did this basically. We'll talk more about it, but I optimized I had to do exponential smoothing there, and the library that I was using, it was like really slow. So I wrote my own code and then optimized it, and basically that's where I picked this activity from. How are you all doing with the coding? Are you all about to finish? Or?
Just the time it works. We can figure
So-
out how time it works.
Oh, which are you using a Jupyter notebook?
Yes.
Oh, just type percentage, time it without percentage, no space, time it,
Oh.
and then call your function.
Oh.
Make a function call.
How can I get the output, but how can I get the time?
Oh, just execute that cell. So here, this is an example. Time it, and then you write the function call. You have to wait like it.
I think we're still seeing your slides, so if you wanted.
Oh, really?
Yeah.
Okay, hold on. I think I shared my program instead of screen. So let me share screen one. Can you all see it now? Can you all see it now?
Yes.
Yeah.
Okay. So yeah, here, Milad. So something like this.
Oh, okay. Okay.
So you write this and then make your function call. So your function call will be your function name and then your arguments. Okay, we have a lot more people now.
Is anyone using a spider as their ID? I think there's a different syntax for time.
Yeah.
Oh yeah, then if you're using Spider, then you'll have to use it as a module. I had a hard time figuring out, like I keep forgetting how to use it in as a
okay.
modules.
Is the when you do percent time it, is that getting the average time? Because I know how to do that. I just wanted to.
No, this is a magic function which implements the time it module actually. So in Spider, you have to do time it dot time it, and then you have to pass your function as a string. But I had a hard time figuring out the exact syntax, so I don't really know. You'll have to check online. But what you can do is you can open up a command line, save your file, open up a command line, and do the same thing that you have done. But if you have Spider installed, you should have Jupyter Notebook too.
Okay.
Likely.
Yeah, I guess I'll switch over to Jupyter.
Yeah. By the way, I don't use Spider because it's it takes up a lot of resources. That's why.
I just love it. It lets you see the variables in real time, which I haven't found a module for Jupyter Notebook that lets me do that this cleanly. Rachel, do you know how many iterations it does when it does the default time it in?
Yeah, I don't know.
100,000. I can just like run it for you here. Let's see. Whatever is default here should be default in that function too.
Okay, perfect.
But I can check it for you. Yeah. It's running. So here, what a million loop it seems actually.
Oh, it's 1,000.
Okay, so everyone finished with
Yeah.
coding it? Okay, let's, before we discuss that activity, let's just go through a demo that I was supposed to do earlier. So here I have written a function that basically squares the element of a list. And I've basically used a for loop to do that. So I have declared a list a squared, and then I'm looping over the elements using for loop, and then squaring the element and adding it to the list. This is my list. Just to check that the results are correct, I call the function. You can see the results look correct. And then I time it. It takes around 1.5 microseconds. The same thing can be done using list comprehension. In list comprehension, the syntax is like this. You basically, everything is inside the square bracket, and then you loop over the elements in the list, and whatever you want to finally have in the list, you write that expression here before that for loop. There are more complex statements where you can add conditional statements here too, but we won't go into that. So just to check that we get the correct result, and then you time it here. So you can see almost 3 orders of magnitude faster. It's taking like 858 nanoseconds, so around 3 orders of magnitude faster than using a loop. One thing I'd like to mention here is that list comprehension is going to be faster if your for loop itself is building the list by appending it to the list, your elements to the list. If your for loop is not doing that, then you might want to time it and see which one is faster, because underlying in the list comprehension, it's actually byte level loop itself. So if your original loop itself is not building up the list, which takes a lot of overhead, that's what takes a lot of time, building the list and appending it to it. Because what happens is when a list is made, you have some memory allocated to it. And as you are building the list, it needs more space. So you might need more space. And so you might have to allocate another memory location and then move the original list to that location. That whole thing takes a lot of overhead. And that's why for loops are slower than list comprehensions in that case. The next is basically using Numpy. As I mentioned before, Numpy is a highly optimized library and uses C code in the background, which is compiled and vectorized. And so here I import the Numpy library and then convert the list into an array, and then square it using the Numpy square function, just to check the results seem to be correct, and then you time it. So this is a bit faster than your list comprehension. As the size of the list itself grows bigger, this might even have like significantly higher, this might be significantly faster than list comprehension. Any questions?
Have you tried just square that? It's my array square instead of using the Numpy square function.
So that function is overloaded whenever you have an array. It will basically call numpy.square in the background. So even if you do my array squared,
yes,
this thing basically calls numpy.square in the background.
Oh, so it's more okay.
Yeah.
Okay.
Or the other way, but both will take similar time. So you can
okay.
It will take similar time.
Yeah. Okay.
Let's see.
Oh, okay.
So one, I don't know which one is implemented, but I am most likely this is overloaded to call numpy.square. Any other questions? Okay, then we'll move on to the the activity. So what did you all like? Who used loops to do the simple exponential smoothing? Milad, anyone else?
I used a loop and then tried to spit it up with JIT.
Okay, yeah. So that was going to be the last one. So Roberta, did you say that you use JIT?
Yes.
Okay.
So in Spider, there was a big improvement when I used JIT. It went from an average of, well, I only had the total time. It went from 4 seconds to 0.2 seconds.
Yeah.
But when I used JIT in Jupyter Notebook, it actually didn't really make much of an improvement. So I don't know what. Maybe I'm using JIT wrong in Jupyter Notebook. Or...
No, sometimes that might happen because it's how it works. But if you run it again, you should see the improvement.
Okay.
But yeah, like that is going to be the last option that I use. But okay, what times did you all get?
We got 31 nanoseconds. Plus or minus 4.2.
Is that with JIT or without JIT?
That's with JIT. Without JIT, it's 35 nanoseconds.
Okay. That doesn't seem to be a lot of improvement though. Milad, how much time did it take for you?
1.5
microseconds, right? Yeah. Rachel?
It took 1 times 10 to the negative 6 seconds, which I can't remember what unit.
But
that
that's one microsecond.
1 microsecond.
Hassan?
I'm using PyCharm, so I was trying to figure out how to find the execution time of my code online.
Oh, okay.
That's the problem, yeah.
Okay. Yeah, it's that time it module you have to figure out how to use it in the modules mode.
Yeah, exactly.
But,
yeah, I'll try to search for something online.
Yeah.
I'll get back to you.
Yeah. So here. So here, let me. So the first function is as I wrote it as a loop. So let's see here. So this is what I get just to verify the results. Time it. It takes 4.97 microseconds on my system using the loop. And then there's a library from stats model, which I import and then use it. The results are correct. Let's see the time. So this one is like even slower than the for loop. So I don't know what the library is doing. And then here I'm using list comprehension. Basically, I reverse the array, enumerate it, and then use the list comprehension. Verifying that the output is correct. Yep. So note that the loop took 4.97 microsecond, while list comprehension takes 6.23 microseconds. So you can see that list comprehension is actually not faster than for loop in this case, because as I mentioned earlier, in for loop, here in this for loop, I'm not building up a list itself as such. So they have similar times basically. And the last one is just-in-time compilation. So I'm using Numbar's just-in-time compilation library. Here, I'm basically just using the same code that I use in the for loop, the same function, just change the name here to JIT, and then adding this decorator to this function. You can look up the syntax here, but there are several options that you can pass. One is this is the default option, which is no Python is equal to true, I think is the default option. In this option, basically, the just-in-time compiler, it compiles everything inside this function instead of, and doesn't use the Python interpreter at all. Now, depending on your code, this might fail, And so you might have to go into object mode, which is the other option, where the just-in-time compiler will decide. It will try to compile your code. If it doesn't compile, then you use the Python interpreter here. So this is basically the same code, just with just-in-time compiler. Verifying the result, 1.14, and so this one takes nanoseconds. Again, around 3 orders magnitude faster than your other options. Just, one thing about it is like, why not use it everywhere? Again, as I mentioned that it has very strict, it has some restrictions, and so your compiler might not be able to compile code, and it will, basically fall back to your Python interpreter, which will make your code slow. So it might not be possible to use it everywhere. You have to check it where you'll have to read the documentation where you can use it and where you cannot. Any questions?
I had a quick question on the list comprehension. I thought, maybe I have this wrong. I thought that since this was like a dynamic program, you couldn't do list comprehension to do this.
Oh yeah, that's why I kind of did some intelligent switching. So I'm reversing the array here. So if you note this down and you can work this out, but this thing will work.
Yeah, it ends up being kind of a cheat to get the.
Yeah, it's like a cheat too.
Okay, I'll have to look into that. I've never seen that trick.
Yeah. Most likely, probably I searched like when I was doing this thing like back in during my internship. I'm quite sure that I didn't come up with this cheat. I probably saw it somewhere and then tried it. Yeah, but because as you mentioned, like I wouldn't even think about a cheat, like since it's a dynamic programming and there's dependency on subsequent iterations, so it becomes difficult to think of these things. But once someone figures it out, you just need to search it. Any other questions? Okay, then next, just an anecdote. Basically, this is back in some undergrad, like I talked to a common friend of friend. Basically, they were using MATLAB for some lab, and this was their last semester summer before they started their grad school. MATLAB and Python are similar things. Python is a copy of MATLAB mostly. And yeah, thanks to Sudesh for saving my soul and my grade. What if you are stuck with a for loop? And this section is basically in general, not just for Python, but for other programming languages too. There's 3 options that I mentioned here. One is minimize dots. Dots are basically your accessor in any object-oriented programming languages. Like for example, in the demo we use numpy.square. So in the numpy library, I'm using the square member method, and so that's dot. Now, if you have something like that, well, before that, the other option is the other tip is using you want to prefer local variables over global variables. Now, if you are, if you have, for example, you are accessing some global variable in your loop, and your loop is being repeated several times, accessing global variable takes quite longer than accessing a local variable. And similarly with dots also, as you have several dots in your code, that reduces your speed too. And if you have those inside your loop, then you want to then that operation is happening multiple times, right? So if your loop is running, say 1,000,000 times, that speed, the slowdown is happening 1,000,000 times. So you want to kind of try to minimize those things. And also, like, if you have multiplication and division inside your loop, those are relatively expensive operations. So there might be some ways to minimize those multiplication and division inside the loop. So let's take another activity. This is more on paper. You don't really need to.
What do you mean by dots? Sorry, I maybe missed.
Dots are accessors. So for example, if you write numpy dots square to square any list, your dot is accessing the member method of square method of numpy library, right?
Okay.
So that's the dot I'm talking about. So as you use several, you might have, for example, in the stats in the library that I use for the simple exponential smoothing, I had stats model dot TSA dot API. So there are 2 dots in there, right? So it gets, as you have several dots, it gets slower and slower.
Okay. Interesting.
So this is just a second activity. Can you optimize the following code? You don't have to code it. You just like it's more of a paperwork and thinking like what you want to do.
For integer I equals 0.
Also, whatever whatever ways you think of optimizing it, like are there any things that you need to be worried about with that optimization that you do?
Divided by a. What's a?
I mean, the first thing, why don't you do like the addition and then divide by a? Because you said like the division takes around like more than the addition. So you add the 2 components and then divide by a. So you save in the number of cycles.
Yes, that's one way. Not one way, but that's one thing that you can
Yeah,
do.
that's like the first thing to do.
Yep.
You can use the comprehensive like square bracket x plus y x. I don't know. No, I plus j I for I in x and j in y.
You can do that in Python, but this is more general programming.
General. Okay.
So in Python, you can change that to that.
If it is also in general, why don't you do the idea of vectorization, the one you presented before?
Not all programming languages have support. You can do that, but yeah, that's one way. But not all programming languages have support for vectorization. And the other thing is vectorization happens by, like in other programming languages, the compiler itself is intelligent to unroll this loop and vectorize it basically. So you don't have to explicitly do it in, for example, Java. So I had 2 things in mind. One Hassan already mentioned. So that was one thing that I had in mind. What's the other thing? So what is one expensive operation that's happening here?
Division.
Division, right?
Yeah.
And how many cycles does division
you
take?
Add them at the end, divide the results after the for loop, because you divide for loop, just get the result, and at the end divide all by a. So you divide 1 time instead of the for loop time.
But there are many. You are kind of close to what I was thinking, but the thing that you have to notice is that you still have, like, if you do it at the end, then you still have to divide it by a, like all the elements by a, right?
Yeah.
I have a question. How expensive is it to invert a component compared to the division? Does it take the same execution time to look at the inverse and then do the multiplication instead of division?
Yes. So that's the second thing. So here, this is what my solution would look like.
But my question is, okay, you inverted only once.
Yeah, I inverted once before the loop, and then I'm doing multiplication instead of division.
Sure.
Because multiplication takes 6 cycles and division takes 30 to 60 cycles.
Oh, I didn't know that. Okay.
Right. So the first thing that you see that you mentioned, Hassan, you put do the addition first, and then instead of division, I'm doing multiplication here. Anything that you need to be careful about doing in this optimization?
Would this lose some precision?
Kind of close. So it's not just about precision, but more about if your B has significantly less number of significant bits compared to the addition of xi and yi, then this might you might essentially be just multiplying by 0. Right. So any other questions? Okay. My final remarks. One is, don't try to optimize everything. Generally you identify bottlenecks in your code using profilers, and then if you are seeing that some code you are doing executing so often, you might optimize those code and not, for example, file operations take significantly long time, but you don't optimize file operations because generally you do that only once towards the end of your code. One other thing that I don't have in the slides is an important thing is depending on like what programming languages you use, it's called something called row major and column major languages. I don't want to go into details of it, but you might want to look it up. That ends my presentation here. Thank you. I'd be happy to take any other questions.
Yeah, I had a question. Well, first of all, thank you. This was super cool and really fun. But I was wondering where you kind of picked this up. It sounds like you were using some of these skills in your internship. Did you kind of teach it to yourself by like Googling it? Did you take a class? Is this something that you learned like in undergrad? But I know it's like not really something that's emphasized in typical ORE classes.
Well, I used to kind of read these online generally, but most of the stuff, like a lot of stuff I picked up, with time. But I got really interested into these things after I took a course called Computational Optimization in fall 2016. It's not offered anymore because the professor is not there. But then I took several courses with TAC through the SDS department. They have some hardware optimization stuff that introduces you to the basics. So the first part of this presentation was basically based off what I learned in those courses through TAC, and others I picked up through time, trying to experiment with code and looking up online basically.
Yeah, very cool. I didn't know. So TAC offers. I've only really heard of TAC. I don't know much about it. Like they have classes that you can take.
Yeah. They offer courses through the SDS department.
Okay.
So one of the courses basically talked about one of the courses that I took. They talk about parallel programming. So there are two paradigms that they talk about. One is OpenMP, which is mostly parallelizing for loops, and then the other is MPI, which is message passing interface. When you have supercomputers, where like different computers are in different clusters or separated, they're not in the same physical unit. How do you parallelize them? So those, and the other was basically hardware optimization. The other course was like they had several parts to it, but one of the component was basically hardware optimization, not basically how to write your code, like basically how optimization can be done through specific to hardwares and all.
Very cool.
I hope you all found it useful, like because this was just an intro class and I didn't discuss a lot of things, but just as I mentioned, I just gave a taste of what's out there.
Yeah, well, for me, this is very useful just to kind of start thinking about this because, usually when I'm writing my code, it's just about having something that runs and doesn't give me errors. But, definitely sometimes time is something that I run into as a constraint. So this is super helpful for me to just kind of start thinking about it and different ways to write my code.
Yeah. And yeah, like that kind of reminds me of, so for example, the research that I'm doing, I initially wrote my code in Python. but then things got complex, and I couldn't find a way to actually use JIT to optimize my code for those complex situations, because the Python compiler, like the JIT compiler, basically would fall back to object mode, and I had to finally switch to Java.
Yeah, thanks, man. Really appreciate it.
Yeah, thanks.
This has been great. If nobody else has any questions, we can end it here. But thank you so much, Sudesh, for doing this. This is really cool.
Thank you.
Thank you. Bye-bye.
Bye.
All right. Bye.